So back to the problem statement. The answer to part A is no, and I've proven it. Now part B, if no, how hard should I push to get it moving? Okay, so how hard should I push to get it moving? So we can just come back here. We can set up the whole problem. We can go down. We can say, now I need to add a push. I need to add a push in order to get it moving. So I'm going to push on this with my hand, F push. And so I'm going to add that to the free body diagram, F push. So now we have 4 forces on it, and the F push is in the plus X direction. You could say, well, how do I know? Well, that's the easiest way to do it. I guess you could say, I could push straight down towards the ramp and at infinity, and it's not going to move. But yeah, it doesn't make sense. Doesn't it make sense if you want to get it moving to push it down the ramp? So F push is in the X direction. So I'm going to add to F net X and F push. And I'm doing this sort of on top of what we already did because I want to show conceptually we don't necessarily have to go through this whole process again. But that's what we add to F net X. The components of Fg are still the same. And now when we get to plugging into Newton's second law, what we get is F push plus Fg minus Ff equals max. So that's what we get, and everything else is the same. Now we're saying we do want the acceleration to be greater than 0. So part B is taking Newton's second law, F push plus Fgx minus Ff equals max, and saying a sub x does have to be greater than 0 in order to get it moving. And solve for F push. A sub x has to be greater than 0 in order to get it moving, and solve for F push. And which friction do we use? If it's not moving to begin with, and we're pushing to overcome the static friction, we've got to use static friction. FFS max, we need to overcome the maximum static frictional force, so we're going to plug in that in order to get that. So this is the idea, is that F push plus Fg has got to be greater than FFS max. That's where I'm trying to get to, is the concept here. We could plug into the equations, but the concept here is that I'm going to add a push down the ramp to the gravitational force, and it's got to be greater than the maximum static frictional force. That's what this equation, Newton's second law, ends up telling us. That in order to get it moving, F push plus the gravitational force down the ramp must be bigger than the maximum static frictional force in order to get it moving. So therefore we can just solve for F push. F push is greater than FFS max minus Fgx, and plug in F push must be greater than mu s Fn minus Fgx. And go ahead and look back at nothing's changed. Fn is still, this hasn't changed. The y equation hasn't changed, right? The y equation hasn't changed. So Fn is still mg cosine theta. And Fgx is still mg cosine theta. So F push must be greater than mu s mg, what was it again? Cosine theta. Cosine theta minus Fg, which is mg sine theta. And so therefore, F push, we can simplify that a little bit, is greater than mu s cosine theta minus sine theta times mg. And therefore, the m's don't cancel this time. We actually need to use mg, and the number is, so F push has to be bigger than or equal to, it doesn't really matter whether we say around 5.94 newtons or bigger. Now that we've given it a little shove to get it moving, and just make sure I stated the problem correctly, we're not continually pushing it. We're just giving it a little push to get it started, right? Just shove, get it started. Oh, sorry, I'm doing hand motions that, like, you can see me. You can't see me. And so then the question is does it keep going down the ramp, or does it come to a stop? And that's, again, why would it come to a stop? It would come to a stop because there is friction resisting the motion. So I just gave it a shove this push is no longer here, and friction is resisting the motion, and it may be enough friction that it slows it down and comes to stop. Or it may not be. Right? But so let's just conceptually, we can go back and just do it with equations, but conceptually think about what's happening. What's happening now in part C is that the component of gravity pulling it down the ramp, there is a component of gravity pulling it down the ramp, and there is friction pushing it back up the ramp or slowing it down. And the question really is which one of those is bigger? So if you see it conceptually, you can just ask which one of those is bigger, and that's going to tell me whether it keeps moving. Actually, if we want to calculate the acceleration, we got to do a Newton's second law. So let's go ahead and just do the Newton's second law to this situation. So let me go ahead and redraw the situation for part C. So this is the situation where the body is now moving and it's accelerating. Acceleration could be 0, it could be traveling at constant velocity. It could be speeding up down the ramp, or it could be slowing down the ramp. And so that's going to tell you the answer to the original question, which was, once it moves, will it keep moving? If the acceleration is positive down the ramp, then that means it's speeding up down the ramp and it won't stop. But if the acceleration indicates it's slowing down, then it will stop. So that's why we need to find the acceleration. So let's go ahead and draw a free body diagram. Even though we've already done it, I'll just redo it real quick. And just repeated all the steps that we did for this problem, just to make it neat again. Draw a free body diagram, choose the axes, draw a diagram, choose the axes, draw a free body diagram, write down Fnet, break it into X and Y components, take all your forces on that diagram and break them into their X and Y components. So we've got Fg has an X component and a Y component. Fill in the force on the left-hand side, and then fill in what we know on the right-hand side. So what we end up getting is Fgx minus Ff equals ma sub x, which we had before. We end up getting Fn minus Fgy equals ma sub y equals 0, which is what we had before. Equals 0 because it's not accelerating perpendicular to the ramp. It's only accelerating parallel to the ramp. So that's what we had before. And so what we're solving for here, what is the acceleration? We're solving for a sub x. So we can go ahead and rewrite this on the next page. Now we just have to recognize, so I just rewrote the equations where we are. We need to recognize that the frictional force is kinetic. So the frictional force is mu sub k Fn, and it's kinetic because the body is now moving. It's now sliding. So the frictional force is kinetic. And so we can go ahead and now plug that in for the frictional force there and simply mathematically, algebraically solve these equations together. We already knew Fgx m and Fgy from before. So now we're just identifying mu sub k Fn, and therefore we can solve the second equation. Fn is equal to Fgy, which from before was mg sine theta, where theta is 25 degrees, making sure we're keeping track of that. Plug that in to the first equation. Plug that into the first equation, Fgx, which is mg sine theta, minus Ff mu sub k, which is mu sub k Fn, and Fn is, so I'm just going plugging in all the way, right? So this is Ff, the second term, equals the mass times the acceleration in the x direction, acceleration down the ramp. And so therefore, the masses cancel, and we get g times sine theta minus mu k cosine theta equals, whoops, no m. The masses cancel on both sides, a sub x, and plug in. So when we plug in, we get a equals positive 0.58 meters per second squared. That's important to get that sign and make sure we understand that that sign, positive 0.58 meters per second squared, means that it's accelerating in the plus x direction. It's speeding up in the plus x direction at 0.58 meters per second squared. If it was negative, it would mean it was slowing down and it would come to a stop. But the answer is positive, so therefore it's going to keep moving. It's not going to stop. That's the answer to part C. Okay, done.